Welcome to today's IEEE Geoscience and Remote Sensing Society webinar. We're so glad you're joining us. United by the mission to advance geoscience and remote sensing, GRSS is dedicated to knowledge sharing by ensuring transparent, accessible, and collaborative learning for all. And our webinars are just one way we bring that commitment to life. Designed for students, early career researchers, professionals, and enthusiasts, these webinars address foundational topics as well as a wide range of emerging subjects, while also offering sessions on academic writing, publishing, and career planning. Our webinars are made possible through the collaborative efforts of GRSS's technical committees and various other initiatives, bringing together a diverse community of experts to deliver high-quality learning content. During the webinar, please submit your questions through the Q&A feature, and they'll be addressed at the end. You'll be asked to complete a survey afterwards, which helps us tailor content to your interests. Be sure to check out the IEEE GRSS YouTube channel for previous webinar recordings in case you missed any. And for updates on future webinars, visit the GRSS calendar and follow us on social media. We're excited to have you with us. Let's dive in.
Okay, so good afternoon or good morning or good evening, depending on your time zone. I'm Davide De Santis, and I'm co-lead the Physics Informed Machine Learning group in the framework of the MIRS, Modeling in Remote Sensing Technical Committee of IEEE GRSS. And today is my pleasure to host this webinar that will be on physics informed machine learning for Earth observation. Just a two quick suggestion insight that I would like to provide to all the audience before starting the webinar, and I will just insert the some links that can be useful for you. The first is for introducing you the MIRS technical committee, where actually the Physics Informed Machine Learning group is it's a working group of part of the MIRS, and on behalf of this we are organizing today this webinar. And if you would like to be involved in the MIRS activity, please I just put here also the link that you can register to be part of the MIRS technical committee. And very last but not least, information I would like to give you is that it's now open and time to submit contribution for the next IEEE GRSS IGERS 2026 conference that will be in Washington next year. And there is open right now for submission, in particular contributing session that is physics informed machine learning in remote sensing. And I leave here the link that you can read the scope and you can apply. Of course, you are very welcome to consider the possibility to send your contribution here. Now, let me introduce with it's a very big pleasure for me introduce you the speaker of today, that is Professor Fabio Del Frate from Vergata University of Rome, and he's professor of remote sensing, and he teaches his experience is a multi-decade experience on artificial intelligence, also for Earth observation application, remote sensing, electromagnetic field. But today will be the focus on again physics informed machine learning for artificial intelligence, for Earth observation, sorry. And now I just leave the floor to Professor Fabio Del Frate. Just a reminder that we have a talk of 45 minutes and then a Q&A session that we will have at the end of the Professor Fabio Del Frate talk. And please, Fabio, the floor is yours.
Okay, thank you, Davide. Also for me, it's a pleasure to be here giving this seminar. and thank you very much for the invitation. So I'll share my screen, my presentation. Okay, hope you can see.
Yes, we can see and
okay.
hear you.
Thank you. Okay, so the topic is a very hot topic, I think, because it's explainable. We are talking of explainable AI. There are many terms to depict this approach to artificial intelligence: physics-based, explainable, and other. Basically, it means not treating the artificial intelligence as a black box, but trying to understand what's going on. Because when you are training an artificial intelligence model, you actually have a big power. You have a lot of capabilities. And it could seem that actually the result at the beginning is very good, they're excellent, because this power of the artificial intelligence. But we have to be very careful, because sometimes if you're not validating, if you're not looking for physical constraints in what you're doing, okay, the results may be very nice, but may not very reliable. So that's why physics-based artificial intelligence, I think, is an important topic also for the future of this technology. You see here my email, so I'm pleased to answer questions, even if not now, in the following days, if you want to contact me for any reasons. So first of all, we are talking about artificial intelligence applied to remote sensing, to Earth observation. And we need artificial intelligence in this topic, because remote sensing and Earth observation, first of all, is a matter of physics. Okay, so there are waves which are traveling, which are interacting with the atmosphere, interacting with the surface, interacting with objects. There are many physical processes: reflections, refractions, scattering, absorption. And the information is there, by the way. I mean, the information in the interaction between the electromagnetic wave and the surface or the object. So we have to be there as well. We have to understand what's going on in terms of physical mechanisms. Otherwise, again, if we are losing contact with physics, maybe what we are doing is not robust, is not reliable. So again, never use like this. Never use artificial intelligence like this. You put data inside, and then you train a very nice model, and magically the solution that you're waiting for appears. This is an example of some how at least a bad communication, in my opinion, is given. So the artificial intelligence is presented as something which can do everything, which can do everything we are expecting, which we would like to see. Everyone would like to see SAR images translated into optical images, into visible images, because we know that visible images are more connected um, to our experience, to our daily experience where we use eyes. But that's not something really, possible if you want from a physical point of view. Okay, at least not possible, generally possible. So if you send a message like, "Okay, we can do this," you are saying something at least on which I do not agree. Okay, because the physics underlying the scattering mechanisms in those two regions of the electromagnetic spectrum are completely different. Okay, so you cannot make a complete translation of this. So at least if you want to propose something which goes into that direction, you very clearly to state the limitations, which are the specific cases where you have the possibility of performing such a transformation. So just to say that AI is inviting us to approach many different problems. But when we are addressing these problems, we have to be stuck to the physics. This is an optical image, a radar image of the same area, by the way, our camps. As you see how much different they look like. So again, I mean, the physical mechanisms are completely different as well. And something which can be seen with the radar cannot be seen with the optical, for sure. Okay, and the same is the opposite. Something that which can you derived from the optical image cannot at all can be seen with the radar. So a translation will be always have some lags, will always have some holes, and this has to be clear. So if you want to be stuck with we need to link the connected with the physics. In the literature, we can find various approaches to train artificial intelligence models in embedding physical constraints. For example, you can put the physical constraint, the physical principles in the loss functions. So of course, you have to define the specific problem. You have to define the specific laws that you want to embed into the loss function, and you train the neural network architecture, ensuring that the model learns respecting the laws of the physics. There are other approaches where physics layers are instead included in the neural network architecture as well. Especially this happens in deep neural networks. So in this case, the general background, which is contained in the physics, is in some way encoded specifically in some network layers. Or you can more specifically encode some differential equations, which are characterized in the physical problems you are considering. Partial differential equations always in deep learning architectures can be seen, and allow also in this case for end-to-end training. This is something that you can find also in this paper. I want to highlight. But in the very end, I mean, the other possibility that you have when you are using the radiative transfer model or physics in the training process of a neural network or an artificial intelligence model is using data which are generated by these models. So at least part of the data concur in the definition of the loss functions, and with that you can have some specific feedback from the physics that you are training with the data which are consistent with the physics, with the laws of the physics. So this is the approach that actually on which I mostly base my experience when dealing with artificial intelligence linked to electromagnetism, because as we said, we are talking of waves which are traveling over electromagnetic waves, and it's very interesting to see how the different electromagnetic models can have various aspects, which kind of problems we have to tackle when we are using these electromagnetic models in the training of a neural network, and in particular in the generating the data that you're going to use to train and validate a neural network or artificial intelligence model. So my talk will be mostly based in presenting some cases where in different domains these electromagnetic rules have been considered, and how the data have been generated, and how we train the model. In generally talking, okay, the problem is we want to know A, okay, let's say a quantity A. The starting point is that B is sensitive to A. A is our final target. So is our applicative quantity that we want to retrieve for the remote sensing data. B is the electromagnetic quantity. So what is measured by the sensor in terms of reflectivity, in terms of emissivity, in terms of backscattering coefficient. So we know that B is some way sensitive to A. What we want to know is A starting from B. Indeed, there is also the forward problem, which is what is B once we know A? Okay, because the forward problem is the basis of the electromagnetic model that we are going to discuss. Basically, the electromagnetic modeling, the physics-based model, is the model which translates, which leads us from A to B. So given a specific geophysical quantity, what is the electromagnetic quantity which will be measured if the sensor is looking at A? So in this case, we are talking of the forward modeling, okay? And the function is f, and so we know that f of A is equal to B, okay? But the inverse problem, which is the applicative problem, which we want to solve with the artificial intelligence, is once we know B, what is A, okay? So in this case, what we're looking at is the inverse functions. So is f minus 1 elevated to minus 1, such that f elevated to the minus 1 of B is A. So basically, we need both models in our case if we want to be physically consistent. We have to know the forward model, which solves the forward problem, and we need to create with artificial intelligence the inverse problem, to solve the inverse problem, to create the solution for the inverse problem with an artificial intelligent model. So the forward problem is represented by functions, this f that I was mentioning, and this is the function is namely the radiative transfer models or electromagnetic models. So once the characterization of a certain observed geophysical scenario is given, the electromagnetic quantity is the electromagnetic quantity. So the forward problem gives us the electromagnetic quantity that will be measured by the EOS sensor, as I was saying before. So, for example, given a certain vegetation status, the forward problem tells us what is the corresponding backscattering coefficients. Give a certain atmospheric status, the forward model gives us the corresponding top of atmosphere radiances. So it's telling us the electromagnetic quantities once geophysical status or quantities are known. This is what the forward problem, the electromagnetic model, does. And the forward model, the electromagnetic model, can be useful under different points of view because they can investigate on the feasibility of the retrieval problem. Is the retrieval problem possible? So don't let the artificial intelligence solve the problem if it's not physically possible to find a solution. So it gives the feasibility on the exercise we are going to perform. They can help data balancing, compensating lags in ground measurements, because of course we need a lot of data if you want to train the model, the artificial intelligence model in an appropriate way. They can help to understand the bounds within which the desired parameters can be retrieved unambiguously, okay? And they can help also in the selection of optimal inputs of the machine learning of the artificial intelligence model. So having, being able to manipulate, to have confidence, even if we don't need to be expert, of course, of the specific problem, but knowing how to manage the radiative model, of course, can help us under many points of view. So we start now some examples covering different domains. I will go fast also because I want to give you an overview of how these electromagnetic models can be manipulated, can be managed in order to generate the data that we need for our artificial intelligence model. First, I think a very interesting experiment, the example has to do with SAR interferometry that, maybe is a very complex, technology in Earth observation. In particular, it is used for estimating also seismic parameters. So here the problem is, given an interferogram which has been produced considering images before and after an earthquake, tell me what are the characteristics of the fault which generated the earthquake. And so in a simplified way, in a simplified scheme, this is what we are looking for, okay? We have an interferogram, we have an artificial intelligence model, and we wanted the model gives us as output some parameters which are characterizing the fault. And these are 6 or 7 parameters typical describing a fault and a seismic events. Of course, the very nice thing of a remote sensing and of Earth observation, and also in using artificial intelligence in Earth observation, is that we cannot do it by ourselves, okay? We need collaboration with the people who are domain experts. So, for example, this work was done in a strict connection with the Italian Geology and Istituto Nazionale di Geophysics and Volcanology National Institute, INGV, because they know very well the forward modeling, okay? Okay, a very good approach, a very good rule is always to train the model with simulated data, but of course you have always to be connected with the real scenario. So if you are training with simulated data, with data provided by a model, a radiative transfer model, you need to, or an electromagnetic model, let's say, you need always to see if the model indeed is something which is reliable or not. So in the end, the final validation has to be done with real data. Okay, this is some very short introduction about the specific problem we were addressing in this case. So these are the 3 families, 3 categories of faults that are generally considered. We are talking of seismic events. So seismic event is generated by a fault, and these are the family of fault, the 3 families of fault, which are mainly, the most important. They are the forward fault, thrust or reverse fault, and strike slip fault. And as you see, they generate different movements of the crust. Okay, so according to the type of fault, the movement of the surface of the layer beneath the surface will be different. Here, what is the forward problem? It's not indeed a radiant transfer problem. It's called rain change. It has to do more with more, to say the truth, with the
I don't know. Sorry, I don't know what happened, actually. The Zoom was suddenly closed.
Could you reshare the slides again, Fabio and Fabio?
Okay. Okay. Now
Yeah, I
I
think
think
it's good.
Okay, I think you can continue, Fabio. Thank you.
Fabio, you're muted,
You
by
are
the way.
mute.
Okay, sorry. So I go on now. So in this case, okay, we have this range change model, which needs some parameters. It depends on the parameters, of course, are characterizing the sleep and the faults. So the fault characterization relies on several parameters. And the values of these parameters are given, the software calculates the displacement. So how the surface moves from the original position. This is the publication, the reference where this range change software is played. And we see here, as in any case forward model, we have the input parameters, which in this case include the fault position, the depth of the of the fault, the length, the wind, the strike, dip, and three components of the slip, while the output consists of the displacement components. So this is the scheme how the displacement components can be addressed. I don't go too much into details, but yes. So what you see here is that the various interferograms that were generated according to the different types of faults, according to the different parameters characterizing the fault. For example, this is a fault with within at 10 kilometers. This is the same fault at 8 kilometers, and this is of course what we are going to retrieve in the end. Once in the end, we have this kind of interferograms, and we want to know, for example, the depth of the faults. Okay, so but here we are the forward model. So once we know the depth of the fault, we want to generate the interferogram. These are other variability according to other parameters of the fault, in particular the strike and the dip angles, which are characterizing the fault, the orientation of the fault. And here is the very interesting step when we are generating the data that we need for the training of the neural network. And that is why we need the collaboration of a domain expert, because by ourselves we were not able to understand what are the intervals in which made sense to generate the data. Okay, we need an interval for the length of the fault. We need a feasible interval, a reliable interval for the width, for all the parameters that we were considering. And so for each of the categories of each of the types of the fault, we were suggested by our colleague Salvatore Strabondo, with whom I was happy to carry on all this study and work, what could be the appropriate interval within which to let the parameters vary. Okay, so once we knew the interval we have to use is input of the model, of the forward model, we could generate different interferograms, so for the different types of fault, and then we can train the network. Okay, so we could train the network knowing the interferogram, having the interferogram as input, but also knowing the output, because it was set by the forward model. In literature, a huge number of models relative to the test cases that we considered were available. I mean, in this case, inverse model. So once we had the interferogram, in particular, once we focus on one specific test case, in this case, it was, for example, the event which happened in Colfiorito. There were different approaches which were trying to estimate the parameters, of course, from the interferograms, but not just from the interferograms. You see, also for other, let's say, type of data, tried to retrieve the parameters associated to that seismic event. And they made it deal with such with a large variability, because of course everything was made of very subjective methods. So there was not an automatic model like a neural network could be, and that's why the study was important. The first problem, we divided the problem into two sub-problems. One was to the definition of the fault mechanism, so to which class the fault belongs. For this problem, we set up a training set of 750 synthetic interferograms and a validation set of 450 interferograms. So in the end, we trained the neural network in a way that it was able to classify between a normal, a strike, or a thrust type of fault. Okay, so the worst problem was fault classification. Then we actually passed to the other problem, which was the parameter of the fault. Here, once the fault classification was performed, and in this case, we trained with 250 synthetic interferograms and tested with 150 synthetic interferograms. Okay, so in the end, we went to the real cases. There was the cases one, there's a Colfiorito event where the neural network was able to classify it correctly as a forward mechanism, starting from the interferogram, and also retrieving the parameters characterizing the fault. In case two, again, was another real case. This was the BAM event. So once it was trained in a way that we said before, the neural network was able to establish the fault. It was the type of the fault was a strike slick, and then in a second step, it was able to retrieve the parameters associated with the fault. And also a third case, with a case of a reverse mechanism, so this side of fault, again, automatically the mechanism was classified according to the specific parameters. So we set up this methodology using, of course, forward modeling, because on one side it allowed us to generate the data, because you cannot, of course, generate so many interferogram associated to seismic events, because you will need many events. But and this is not the case. So but with a forward modeling using this range change software, we were able to generate the data and also to train the neural network and to test that the neural network when considering real interferogram was performing well. Okay, a second domain is atmosphere. Here, the forward problem is interesting because once we know the atmospheric scenario, we have to understand what are the main electromagnetic quantities that can be measured. So here we set up a simulation based on the reconstructing profiles of temperature profiles and using and the characterization of atmospheric profile, not temperature. The characterization of atmospheric profile is based on profiling it with several variables, typically temperature, pressure, water vapor density, but also other input parameters have been considered for the model, as you see. And the model, in the end, were able to compute the brightness temperatures at the top of the atmosphere. Also in this case, you have to generate many data. So you have to generate profiles, some atmospheric profiles How to do this? If you want to make, of course, something which is consistent, you have to be very careful to take into consideration many effects. For example, for temperature, you have and to also to guarantee fluctuations and variability of the data. You have to superimpose some effects like Gaussian distribution at ground level, or random fluctuations to the temperature value using a gamma distribution. And to be physically consistent, these fluctuations were added to a projected adiabatic profile, and also ground-based thermal inversion should be considered to increase the variability of the atmospheric profile. That here the retrieval was based in water vapor profiles and liquid water profiles. So, of course, also here you have to be careful in generating the data that you used for performing the training of the neural network. So these profiles were constructed and adding random irregularities for water vapor and for liquid water. There was some physical also approach for the thickness of the clouds. We are talking of not precipitating clouds, so, by the way, so the problem was kept a little bit more simple. Of course, here you had in the end to look for what are the best quantities that you want to use as input in the retrieval problem. Okay, so once you have generated the data, you have to understand at which frequency you want to perform, which frequency you want to consider to perform the inversion. So in the inverse problem. And here we see there are very rich microwave radiometer with 7 channels. There was a version with 2 channels, also the possibility of oscillometer. And these are the results, okay, which are very good in terms of estimation of the integrated water vapor and of the integrated liquids. This is the comparison with some real regression model. So the artificial intelligence went much better. But again, here all the work was generating the brightness temperature at the top of the atmosphere and generating all the profiles, the atmospheric profiles, which were corresponding to the brightness temperature that would be measured by a satellite. Okay, so all this approach or this methodology was done for this. Here instead we have another domain which is always atmospheric but more focusing on air quality. And this is the very step that have been used to set up a neural network which is able to estimate concentration of ozone using satellite data. Okay. Also in this case, we use the forward model. So starting from profiles generation, we simulated the radiant spectra that will be measured by the satellite, and then with this data we trained the neural networks. There were several steps. At the beginning we trained the data with all the frequencies. Then with an extended pruning procedure, which I will show in a moment, we selected the frequencies or the wavelength which had the more information contained, and then we retrain the network only using this final selected wavelengths. There are many, there are various radiative transfer models in this spectrum part of the electromagnetic spectrum. In the previous case, we were talking of radiancy, brightness of temperature. We were at the microwave. Here instead we are in the visible infrared, near infrared, and also the ultraviolet. So this is a list of models that I mentioned just to, if you want to look for them. Some of them are very famous, some less. But here, of course, the core of the model is the radiative of the radiative transfer model is these equations, okay? Where L is the radiance in the position, and beta is the volume extinction coefficient, and J is the so-called source function. So basically all the models are implementing this expression, okay? Okay, this is the scheme of a model, in particular of the Liberatran model. So again, you need to set up the profiles, the atmospheric profiles. You have to describe the atmosphere. So then once you have the atmospheric profiles available, you compute first optical properties, and then through the radiative transfer equation, you solve you compute the radiation quantities. Okay, so the model output have radiances and all the other electromagnetic quantities. There are other simulation issues, the solar zetting angle position, the spectral resolution of the sensor that you want to simulate, the noise, which is wavelength dependent, and also the discretization of profiles. So we have to go through these issues before starting the final training. Here is how an extended pruning procedure works. That basically you are looking for the connections. We have more saliency, which are the most important. Typically, this is just analyze looking at the coefficients which are characterizing the connections. So if you remove the connection with the least values, with the values which are the most, let's say, with the minimum quantity, okay, in the end you will understand which are the most effective inputs. So doing like this, in the end we were able to remove many connections. And we were able to retrain the network with the most effective wavelengths. This is a scheme where you see with the gray, you find the band where more many of the wavelengths selected are belonging. Okay, so the gray level is indicating the part of the electromagnetic spectrum, part of the spectrum where there is more sensitivity. So it's according to this principle, you make the selection, the final wavelengths. These are our results, which I will go very fast. In any case, it's just a comparison between what was retrieved by the neural network, which was trained with this procedure, and ozone zones, which are ground-based, and you see there is a good agreement. This is another example of application of AI algorithms where you need first an approach based on radiative transfer, because we are talking here not of ozone, but of particulate matters. And this is a tough problem that we try to face using hyperspectral data, satellite hyperspectral data of Prisma, which is an Italian hyperspectral mission which carry an hyperspectral instrument. And also in this case, we made all the simulation of the physical-based approach using a radiative transfer model, and also transport chemical, as you see, chemical models. So first, a generation of statistically significant set of atmospheric profiles using chemical problems, and CAMS, the Copernicus Atmosphere Monitoring System, which were providing some initial profile with the ground truth, with the content of PM in the profile. And then using a radiative transfer model, we went to simulate the data that would be measured by Prisma. Okay, so we had again the matching between the simulated profile and the simulated data profile that would be measured by the satellite. And using this, we generated and we trained a neural network, and we, again we tested on real cases using, by the way, in this case, also UAV system. This is the general scheme of the model. Again, it's very similar to what I showed before. So we have to characterize the atmosphere. In this case, from the point of view, the PM concentration, and then we go through the various steps, in particular using the radiative transfer model, which gives you the prisma-like irradiance. This is again how we selected in the end the wavelength which are more sensitive for this specific problem, using basically the same kind of approach that I was showing before based on the pruning, extended pruning. And this is completely another scenario, but it's always the same. I mean, you need a model. In this case, it's a scattering model, the Vergata model, which has been developed during many years by my colleagues. So in this case, we want to estimate soil or vegetation parameters. So you need the model which represents the vegetation, and you need the model which allows you to simulate what would be the backscattering coefficients that will be measured with that specific vegetation scenario. Okay, this is how the model works. So it's basically approximating the stems with cylinders and with other kind of approximations from a geometrical point of view. But I don't want to go into details here. Then there is a matrix doubling algorithm which compute basically the final response of the vegetation in terms of scattering. You need also here to generate the data being consistent. So if you want to simulate vegetation, you have to associate with vegetation several parameters. You cannot do it randomly because there are some parameters which are correlated. So the stem radius and the stem height are correlated. So you cannot vary them casually, but you have to keep consistent with in this case more with the physics with the biology. Other parameters you can vary more, let's say, with more degrees of freedom, and you can use allometric function, of course. This is the matrix dynamic algorithm, which is the kernel, the core of the model, which simulates the scattering. But okay, it's basically of different layers, the layers of the trunks, of the stems, and the layers of the leaves and of the branches. So you basically some different contributions. These are the simulation data set. So the simulation of a soil moisture contents corresponding to different frequencies. So starting from the soil moisture content, you compute the frequencies at two bands, at the backscattering coefficients two bands, and also making the degrees, the angle of incidence vary. So we provided a lot of, we generated a lot of simulations based on the C band and L band, where we have solved the forward problem. So once the soil moisture is known, we compute the backscattering coefficients. And this is the estimation once you have trained the model with this generated data. This is how actually you obtain something which is consistent with physics, because basically they connect this on the right side of the picture. You see the coefficients. These are the different coefficients associated to each of the connections. And you see the highest values of the coefficients you find connected to the input, which have the most the more content from in terms of information. Okay, we know that especially where vegetation is above the ground, the L band is very much important, maybe more than C band, and this is reflected into the map of the coefficients which are characterizing the networks. So and this is very nice because actually the electromagnetics in some way is mapped into this coefficient, into the coefficients of the neural network. So let's say the neural network inside of them, when you were inside of the network, we have regenerated, reconstructed the electromagnetic knowledge. So this is another example. Basically, it's always the same, but this time is the final aim is the estimation of biomass of a forestry, in the forest case. So again, we have to generate the backscattering coefficient simulated, starting from very different scenario. So we varied the soil moisture. We varied also the understory, which is a small vegetation above the ground, aside from the vegetation of the forest, so the big trunks, let's say, of the big trees. So we generated different amounts of this understory. We generated different level of speckle noise. So all the data were generated using an electromagnetic model I was mentioning before, the Vergata model, starting from different scenarios of the vegetation. And in the end, we trained the model during the artificial intelligence model with this generated data using the forward modeling, and this is the final result. So it's a nice final result because of course this is as always tested on the real data. So there was a collection of data that was available about the biomass of different forests. So you see the scatter plot is showing a very good pattern. And also here with an extended pruning, we understood that the most important content was coming by the input associated to the P band, which we were expecting from a physical point of view, as we were talking of forest biomass, and we were using either P and L band. Just to conclude, it could be interesting to also to use a neural network, so artificial intelligence for forward modeling, because usually when the forward models that we have seen, of course, use a very, complex equations, and sometimes they may require very high effort computational burden in terms of CPU, for example. So the computations and the burden could be very high when we want to run the forward model. And also, if you think of it, models or no advantage is taken from previous simulations in similar cases. So if every time, even if the input changes a little bit, you have to run again the models. So this was an experiment where actually we were using artificial intelligence model to simulate the radiative transfer model, so to simulate the forward model. So artificial intelligence used as a forward modeling. The input, so where the input of typical input of a model, which are frequency, incident angle, canopy height, in this case, soil surface, the roughness, so standard deviation, correlation length, and volumetric soil volumetric moisture, and the output that we want to generate were backscatter coefficients at different polarizations. So the training patterns were generated according to several variations. So that this is how the variations, the intervals of the input parameters were fixed. And in the end, we had a very interesting result because the error that we obtained using the artificial intelligence model were less than an error considered using a lookup table. Okay, we were of course wanted to estimate some quantities which were between the parameters that we have used for the training. Okay, and everything was much easier. In the end, the number of data to be stored, consider the lookup table were 486 against 80. So also in terms of storage of the model, there was an advantage. Okay, just to conclude, we can say, okay, we start from physics, and physics is known. What is the artificial intelligence that added value? Okay, mainly the added value relies on discovering hidden relationships among the data, which help in the solution of diverse problems, which were not, let's say, visible at the beginning, but of course they can be always physically consistent. And also this could be interesting, artificial intelligence, as we have seen, can be used to represent in a more immediate way the forward problem itself. So this is my last slide, and I thank you very much for your attention.
Okay, thank you very much to you, Fabio. And now we can open the Q&A session, and you can insert your question here in the proper box, which actually or ask it directly, raising your hand. There are already two questions about in the Q&A form that I don't know, Fabio, if you are able to.
You see that on the chat?
Yeah, there is a
Six.
Q&A. There is a Q&A label box on the bottom bar with
Okay.
with
On the
actually there is a
bottom, yeah.
number
Okay, it was in
2.
Italian.
Okay. That
So,
is they're a bit long actually, but the first part is more a comment on what you emphasized. I don't know if you want to
so what should I
quickly
do? I
read.
should do I go through the question and
If maybe we can address this. Or
okay,
we
even when physical laws are integrated into neural network, input data can be can deliver consistent output that predict. So yeah, I mean, I think it's not a question; it's more a comment. The first one.
and then in the part in the part 2
Ah, in the part.
at the
Okay,
end
sorry.
there
Okay.
is the final part is a question.
Yeah. Physics-based
Kuda Kovina.
AI and semantic control systems. What I think is that should I press risposta dal vivo, Davide?
No, I think that you can address directly
Okay. Well, I
speaking
think
right
that
now. Yeah.
among these two parts, I mean, this according having a picture of these two blocks, let's say, the blocks which is the retrieval, the physical consistency, and the semantic integrity. I think they are both are very much important. Both are very much important. But both are very much complex, and I think that I mean they address two specific aspects. The physical consistency, I think it's that you cannot do without. Otherwise, I mean, especially if we are talking of disaster management, otherwise you are really can take decisions which cannot be, I mean, 100% reliable. I mean, maybe in any case 100% is not easy to reach, but you have to be very, very careful. So I think physics must be there undoubtedly. And the semantic integrity, it's a problem that I understand, but I know less. Of course, also, I think it should be very, very important because you cannot allow yourself to, to put uncertainties in terms of misunderstanding, if I understand, if I understand the problem. And so the semantic integrity is also very important. I don't know how much, if we are talking of disaster management, we can leave all the procedure, so the chaining of the two aspects, the physical consistency and the semantic integrity, to an automatic approach, so to a machine. I don't know how much semantic integrity in this case is, essential. Because if you're talking of disaster management, I think that you cannot allow any kind of misunderstanding. And this could be the risk using semantics integrity, if I understand well. So I would give a little bit more weight and importance to the physical parts. I don't know if it is answer more or less Birgit.
Yes, I think so. Actually, there is a second comment for the same yeah, participant, which actually yeah.
Do I go through the second?
Yeah,
There are
there
also
is
people
the
who raise their hands. I don't
yes,
know.
maybe let's come back later to let's
Okay.
priority let's switch to raised hands, and so we have uh-huh, let's see on the participant. We have the first hand from Karim Gonzalez. Please, if you want to, Karim Gonzalez Zucoroto, so if you want, you can talk now. I allowed you to talk. Are you here?
If it's Karima,
Oh,
she's muted.
yeah, I see.
Karima,
Okay,
you're
let's
muted.
go. Yeah.
Okay,
Oh,
meantime, I read
oh,
the other
okay,
question.
okay.
Uh, so,
But we can, or we can go through the second hand, as you prefer.
probably it's the same. Maybe now I start reading
Okay.
this. If you, okay, is Yash Ray. As we know that for training a deep learning model, we usually need a large amount of data. So we implement a physics layer in those models. There are any chance of less requirements? So okay. I think that for deep learning, especially if you are talking of deep learning application in parameter retrieval, because you have these two classes of problems. Okay, classifications and image classification, image object detection, and parameter retrieval. Okay, for image classification, image detection, image processing, maybe the quantity of data can be, for training a deep learning model, can be in some way generated by human beings, there are some data sets available, or by the researchers. But I think that for parameter retrieval, geophysical parameter retrieval, either in the context of vegetation, or let's say of Earth surface, or in the context of atmosphere, or also water, ocean, I think the importance of a physical model which helps you in generating at least some of the data, some parts of the data statistics where you lack something, it's unavoidable. I mean, it's of course you can get better accuracy, but I think it's almost mandatory to use a physical model because all the variability of the parameters and of the scenario has to be taken into account from. So you have to generate data which are statistically significant. And you cannot do it maybe without a forward model. So this is for a Yash Ray.
Okay,
I don't know.
Yeah, I just actually wanted to share my screen to allow people seeing the presentation, but I think I have I had to see the question. Sorry, but maybe I can read it. Okay, that was okay.
Anna?
Karim then wrote the question on the chat. I don't know if you are able to see now in the chat. Uh, is um, is it feasible to use products derived from coherence change detection processing to train a neural network aimed at improving the detection on classification of damaged buildings in conflict-affected environments?
I was looking
Is in the
for the
chat.
chat.
Yeah, is actually is following the question you answered, the last question you answered.
Because I don't. Okay. I don't see the question and answer anymore.
Oh no, because there are two boxes. One is the webinar chat where there are
Okay.
some questions.
Okay, I see the Karime
Okay.
question. Is it feasible to use product derived from coherence change the example processing to train an algorithm to aim at improving it? Well, the point is that you can use whatever you want. I mean, of course, it makes sense to use coherence change detection products. The point is that if you decide to put this information into the model, this could be forever. I mean, the model always will need that. So you have to be sure that you have this coherence change detection always available. And once you have that, yes, I think it's another piece of information that you can exploit for improving your results. But you have to be careful, I mean, to be sure that you have it available. Okay.
Thank you. So there are now one more question in the webinar chat and another couple of questions in the question and answer. So how you prefer?
Okay, let's see if
because there is one now from AI Yadav.
Okay, I'm working on soil moisture detection. It's using sentinel images, supposed to apply transformers. Yeah, for sure. I think it's possible. The point is that for this specific case, for example, the soil moisture retrieval, I really recommend the use also of radiative transfer model, because with them you can really make your data set training more consistent. And by the way, if you are using soil moisture, I don't know if it's bare soil or vegetative soil, but in any case, okay, I show a very complex model regarding vegetation, but there are also other models which are easier to be implemented, and I would really suggest to use them to at least check if what you're doing is consistent from a physical point of view.
Okay, before going to the next one, there is just one more raised hand that maybe we can address, just a raised hand. Which actually Raghavendra actually wrote in chat as well. So that I think is the question.
Okay, so let's go
is
with
how
Raghavendra.
how can glass box machine learning models be employed to detect and explain climate anomalies while providing transparent reasoning behind the predictions? So it's about glass box machine learning models.
But I think that's the important is to have models, and there are also in the case of climate change, there are models which take into account the most important variables which are affecting climate change anomalies, and they are available. I don't have much experience, to say the truth, with the glass box machine learning, but for sure you can find, for example, FAO has been working a lot on this kind of models, and that could be very important again, to make everything consistent. There are models which are working on stress, how variables are stressed by climate change anomalies in different domains, in the desertification and others. So I think I will have a look at this kind of models, because I think they could give a very good clue to navigate also in this field of machine learning, glass box machine learning.
Okay, now if you could go open again the Q&A box at the bottom
Yes.
bar, there are a few remaining questions. I would say that we can address. We will try, and then maybe then other question. I think you shared already your email, so I think that people could also send it by email. But let's try to address from Anna Silva, because the previous you already addressed. So we have, if I want to apply this idea to differentiate crops from SAR data, for example, would phenology be the physical layer? And if I understood, would it be possible to select the best data among the entire year of data based on the crop phenology to differentiate them?
Yes, I mean, if we are talking of crops classification from SAR, and you want to set up using artificial intelligence, and you want to set up a model to generate the training data, which we want to exploit for the training phase of the artificial intelligence model. I think for sure phenology is very important. It's not the only physical layer, because the other physical layer is the electromagnetic part. So how much would be the backscattering coefficients? So the Sentinel-1 backscattering coefficient measured by Sentinel-1 having a certain type of crops with respect to other. But of course, if you are making a multi-temporal, if you're using a multi-temporal approach where phenology is important, it should be included into, let's say, the model, in the modeling of the data. Yes, also to select would be the best dates. For this, again, it's also important to do to work not by themselves, but what expert of the domain. So I would involve a biologist, some agronomy people from the agronomy, because they can tell you many things. So again, our topic, our Earth observation is beautiful because it asks us to work together with other people from other sectors. And this is for artificial the intelligence, it is also more important because if you want to make things again explainable, physically consistent, you need their input. But of course, phenology is important, it should be included.
Okay, thank you. The next one is from Michael Marsalek, and are there any planned or current projects where physical models are used to generate synthetic data to?
Yes, I think this is a very good, nice question. The answer, to be honest, is I don't know, but it has to be like this. I mean, you cannot escape from using synthetic data in foundation models, in particular in foundation models, because foundation models have the ambitions to cover a very wide range of situations. That's why I call foundation. And so it would be really not wise discard the opportunity which is provided by physical models. So definitely if there is any project which is not using physical models in to train foundation models, I don't think they are good. They are working in a perfect way. So again, I mean, also foundation model. This is not just computer science. Okay, this is if we're talking of foundation models in Earth observation, this has to do with physics. So you cannot just take the data and as with a big quantity of data and generate and design the foundation model. You need the physics inside of them.
I had a small network issue, but I think you were finishing answering the foundation models question, right?
Yes, there is a Martin.
Okay. Martin Bayala.
Okay, regarding the scatter portion in saturation, I received an effect when retrieving kind of a water content. Do you believe this is a hard physics? Yeah, what the sense? Yeah, that's a nice question. That's a nice question. I mean, there is a physical limit. So actually, the bigger is in our case, the bigger was the biomass of the forest, and the higher is the limitation of the sensor. So the sensitivity of the sensor gets worse with a very big signal. And maybe with the canopy water content, it might be a little bit different, but of course, this is a physical limit of the more yes of this. I would say it's a hard physical limit to sensor. This is true. So artificial intelligence can help, but cannot. I mean, cancel this problem. It will be always there. And I think it will stay there also if you use deep learning, because doesn't mean that very complex architectures can solve a very complex, I mean, an inherent problem, a problem which is inside the physics. More than deep learning, I think that what can be helpful is to add other pieces of information. For example, I don't know, some other sensors. I'm thinking of LiDAR, for example. So here there is really a gap of information that if you're using especially SAR, that to overcome that, more than using complex architecture or deep learning, you have to add real information.
Okay, I just would like to say that maybe you could stop to write additional question, and maybe additional question you can address, you can send directly to Prof. Fabio del Frate mail that someone just insert right now in the chat. So maybe we can address the last two and then there's a last one in the chat. So last three question, and then we will close the webinar, and all the question. I'm sure that the professor will be happy to reply by email in case, as you prefer. But I think we are going.
Yeah, it's okay. We the last three.
Yeah. So the next is Tiangang.
Yes, I've read it. Yeah. Okay.
Yeah.
Well, it depends. I think it always depends on the problem that you want to address. The complexity, of course, adding complexity many times implies to be very specific. Okay. So if you want to keep a general, I don't think you need much complexity. If your problem is a general, I mean, is a statistics of the problem is not being the characteristic is not being very detailed. I think also a physical model, because always you have to use it, which is simpler, is effective. If you want to, of course, address a problem which is very complex, if you want to address a problem in the vegetation, you want to distinguish between very similar vegetation, you want to distinguish or would want to estimate biomass of some physical parameters in very, let's say, articulated vegetation with many stems or many branches. In that case, maybe you need a more physical problem. I think the complexity goes with the difficulty, with the complexity of the model goes with the complexity of the problem that you want to solve. And in many cases, we do not need a complex model because we want to stay general. Okay, this is for Tiangang.
Yes.
For
And
Abhishek,
last in the Q&A is Abhishek. Yeah.
Heteroscedasticity. Where a larger true yes.
It's about feature importance. Plot. Also give us wrong impression. This is specifically for biomass.
Okay, let's say I think you are referring to this let's say saturation problem that I was mentioning before. And as I was saying before, there was a problem which is a limitation, is a physical limitation that we cannot avoid. But using the artificial model, a little bit this was mitigated. So I think that results still could be, meaningful, also in terms of the input feature importance. Because in any case, the final result, even though there was this saturation problem, were effective, were positive. And so also the consideration in terms of the feature importance could be, I think, be reliable.
Okay, perfect.
Well, yes, something like Monte Carlo, basically, to uncertain quantification. This is a very good technique.
Okay, thank you. And the last question is now I read it from the chat, not from this question answer box, which actually is from Lankashmikant Tiwari, sorry for the pronunciation, and this: how would you design a training strategy to ensure model reliability? Sorry.
Well, the point is everything is rather than in the training, of course. I mean, a lot of the reliability is in the test, in the data that you choose for the validation. Okay, because I think there are always the three sets. One is used for the training, the other is used for the optimizing the topologies of the model. And aside from these two, you have to consider a third one, which is the real flag, is a real response to the effectiveness of your model, to the reliability of your model. So you have to ensure the model reliability, you have to select very let's say very accurate validation points, and not only accurate but also statistically significant. So you have to collect validation points and examples that cover all the statistics of your problem, and therefore that which are reliable. So that's the final let's say the final question to which you need to reply positively if you want to be sure you have a good and reliable model.
Okay, perfect. I think that we address all the question, and I invite again all the additional question to be sent by Prof. Del Frate by email. And now I just would like to thank you very much for the
Thank you to
presentation
you.
and this very fruitful discussion in the Q&A. And with this, I think we can close this webinar. And please, if you are interested, visit the MIRS Technical Committee page on IEEE GRSS, and the Physics in Machine Learning also group will be there. And see you in the next webinar, and have a nice continue of your day, and bye. Goodbye to everyone.
Bye. Thank you. Bye everyone. Thank you.